Okay, hello everybody. So, last class on plain Khovanov homology. I'm not sure what we'll do next class, but it will not be plain Khovanov homology. Okay? As for plain Khovanov homology, I just wanted to give a few examples, and say, but maybe I'll start with the big open problems. So, the first one is a 3D interpretation. So, as it is, the definition of Hovanov homology is completely two-dimensional. Like, you project the knot to the plane, and then in the plane you do some things, and then you prove that it's invariant under planar moves, but so there's no a priori reason why it will be. There is no philosophy, okay? It just is. And in fact, the same can be said about the Jones polynomial, but the Jones polynomial does have other perspectives, and I'll mention them later, and which are more three-dimensional. So, I think that's a pretty big open problem. I mean, it's not sort of a well-defined problem in the sense of, like, here is a statement, is it true or false, okay? But it's still a problem. It still bothers us that we don't know it. If you look at physics papers by Witten and other people, you'll find that there are interpretations in terms of quantum field theory. I wish I could give a class on quantum field theory, but whatever you do with quantum field theory should not satisfy you as mathematicians. Okay? It might be an interpretation, but until you expand it into human-sized mathematics, as opposed to infinite dimensional path integrals and things like that, it's to me it counts less. I wouldn't say it doesn't count, but it counts less. Second problem is, so there is this theorem of Kronheimer and Rovka that I mentioned last time, which says that the Hovanov homology of a knot is equal to the Hovanov homology of an A-knot, which is just the vector space V. If that is the case, then the knot is trivial. And again, so this proof is completely rigorous, completely mathematical. It uses, however, it uses, the technology is insanely complicated. It uses Higard-Floor homology, it uses spectral sequences, it uses analysis at the end, because Higard-Floor homology uses analysis, and there ought to be a much simpler thing. I mean, Hovanov homology, after all, is about when is a knot trivial? So if a knot is trivial, it means that you can present it as the boundary of a disk in R3, okay? Which is not self-intersecting, which is embedded, okay? Because if it's trivial, it's equivalent to the A-knot, and the A-knot is the boundary of a disk in R3. So there is so a knot is trivial if there is a disk in R3 whose boundary, an embedded disk whose boundary is that knot. Now, take that disk and squash it to the plane of the knot, of a planar projection of the knot, and you'll see something that can somehow be decomposed into a union of cycles that cover the faces in the knot projection. Okay, so it ought to be possible to say, and I wasn't precise because I can't be precise because there isn't such a proof. as the one I'm hoping for. Okay, but one can hope that basically, you know, each smoothing in the Hovanov complex of a knot can be interpreted as a small disk, and maybe the arrows going between these smoothings can be interpreted as some directions how to glue them or something like that. And then out of the fact that the Hovanov homology is trivial, you may be able to get a proof that that such a disk exists, a construction of such a disk. Or you know what? Let me say it differently. I mean, suppose you know that the Hovanov invariant of a knot is equal to the Hovanov invariant of an A-knot. Can you constructively construct a way of deforming that knot into the A-knot? And I don't think anybody knows, and you know, if you want to do something useful for your PhD thesis or after, you're welcome to do it. Okay. So that's the philosophy, and now I wanted to show you some computations. So maybe first of all, here is the Hovanov complex of the trefoil knot shown in full. And the only reason I've put it is so that you appreciate, or you get a feel for what it looks like. Okay? So let me explain this picture. Okay, and again, it's really for fun, okay? So first of all, here are the 8 smoothings that make the knot. So this is the 0, 0, 0 smoothing, this is the 1, 1, 1 smoothing. They come in the same order as in previous pictures that we've been looking at. So you should recognize them. Now, look for example at this picture. This picture has 2 cycles in it, so the vector space corresponding to it should be V tensor squared, and in fact with a degree shift of 3. Okay? So, I mean, just look it up in the previous pictures and you'll see it. So, V tensor squared has 4 basis elements. Namely, V plus tensor V plus, V plus tensor V minus tensor V plus, and V minus tensor V minus. So I've written them here as 3 plus plus, 3 plus minus, 3 minus plus, and 3 minus minus, where the 3 stands for the overall degree shift, and the first plus stands for the vector sitting on the cycle labeled 1, and the second sign, not necessarily plus, stands for the vector sitting on the cycle labeled 2. Okay? And now you can easily read the degree of each vector. So the degree of the vector 3 plus plus is, since the shift is 3, and V plus and V plus are each add 1 to the degree, this vector here is of degree 5. So the 3 plus plus is of degree 5. And likewise, the 3 minus minus is of degree 3 minus 2, so it's degree minus 1. And I've color-coded, so okay, I did the same for all spaces, and I've color-coded their degrees by in fact, the colors of the rainbow. So degree 1 is purple, then degree 3 is blue, then green, then orange, then red for degree 9. So maybe you should look at the screen share, because I doubt you can see it on the video camera. Okay? And then I drew arrows to represent the differential. So, for example, the arrow going from here to here is an arrow in which you merge 2 cycles. So it's a multiplication map. So if you multiply v plus by v plus, you get a v plus. So it lands on the vector 4 plus, right? Where the plus stands for the v plus of this vector space. If you look at 3 plus minus and multiply and go this way, it lands on 4 minus. And so on. So I've drawn all the vectors and all the differentials. Now, in principle, I should have signs. But I figured it will make the picture too cluttered. So let's pretend that we work over z mod 2. So the signs are irrelevant. Okay? But in principle, some of these arrows should have signs marked on them as well. Now, if you look at this picture, it is really 5 separate pictures. There is the purple picture, the blue, the green, the orange, and the red. And that was the point, right? Khovanov homology is really 5 complexes, each one giving you one coefficient of the Jones polynomial. Okay, so now what's the homology? So, I mean, with current technology, I mean, at the moment, I'm forced to basically pick a color, let's say green, and then rewrite all the differentials as matrices. So, right, for example, going from here to here, there are 1, 2, 3, 4, 5, 6 greens here, 3 greens here, so it will be a 6 by 3 matrix. I could compute its kernel, I could compute the image of the previous one, I could compute the homology, and in fact I have a computer that can do that. And in fact I'll demonstrate it in a minute, but here I just put a screenshot from a computation. So you load the knot theory program, and then you tell it to compute the Hovanov homology of the PD notation of the mirror of the knot 3-1, because this was the knot we've always used, but was actually the mirror of the standard trefoil. And I want to compute the answer as a function of q and t. But first, let me explain what it means. So basically, there is something you could call the Hovanov polynomial of a knot. So the Hovanov polynomial of a knot is defined to be, basically it's the generating function of all dimensions. So it's the sum of a variable t raised to the power r times the q dimension of the rth homology of the knot. Okay? So if you look at the coefficient of t to the r, so the coefficient of t to the r is the dimension of hr, the degree, I wanted to say t to the r q to the d is the dimension of hr, the degree d piece of it. Let's verify it. Okay? So let's look again at the complex and start with the easiest color. The easiest color is purple. Purple has only one vector, and it's the minus minus vector. The maps coming out of this are multiplication maps. V minus times V minus is equal to 0. So no arrow comes of this vector, comes out of this vector. Okay? So there is a kernel over going from here to here, namely this vector 3 minus minus is in itself in the kernel. And there is no image leading into it because there are no spaces to the left. So in degree 1, this is the purple complex, in degree 1, the homology is one-dimensional and it's concentrated in H0, the zeroth homology group. So purple, so I don't have purple. I'll circle it in red. Purple corresponds to this term here in the computation, right? Degree 1, t to the 0. Okay? Let's look at the next easiest thing. So the next easiest thing is, it's equally easy, the degree 9 piece. So there is only one vector in degree 9, it's the 6 plus 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 vector, and it is in the kernel because there is nothing on the right. It is not in the image because there is nothing even red on the column to its left. So it's a homology class, and it's in degree 9 in H3. So that's that term. The other terms are harder. So let's look, for example, at degree 7. Degree 7 appears here in 1, 2, 3, 4, basically only in this part of the complex. Here, it's a three-dimensional space. And if you look at this so it is spanned by 3 vectors. And if you look here, it is also a three-dimensional space. However, here, each vector maps to the sum of 2 vectors here. Not however, sorry. Each vector here maps to the sum of 2 vectors, and they're always different 2 vectors. So, I mean, it's a different pair of vectors if you start from this one, or from that one, or from that one. So the matrix, so the purple matrix, is the matrix, basically the anti-diagonal matrix. So it's the matrix that has 2 1s in each column, but not the same ones. This matrix is non-singular, so its kernel is 0, and its image is everything. So homology dies, right? The kernel here is nothing, so there's no cycles. Everything here is a boundary because the image is... So homology dies. So the conclusion is that there is no homology in degree 7. Indeed, there is no q to the 7 in this. Okay?
I had a question.
Yeah.
In principle, there can also be torsion, right?
There could be torsion if you're working over Z, yes. But I'm actually now computing over Z mod 2, which is a field.
Yeah.
And, okay. So the remaining 2 terms, unfortunately, are, you could play with them actually. I think the degree 3 term I could actually see by hand, and the degree 5 term is the truly messiest one. Okay, in principle I could also write the matrices, but it's a pain. Okay? So maybe I'll make one more comment before moving on, and this is, so what happens if you take the Khovanov polynomial and do the substitution, t goes to -1. Then t to the r becomes -1 to the r, and that's exactly the Euler characteristic. So this is the Jones polynomial. And you can check that indeed if you replace t by -1 here, you get what we computed before to be the Jones polynomial of the trefoil. Okay? And now I want to show a few more examples. And oops, sorry, the other examples are on another screen. Let's bring them here. Oops, no. Wait, where are they? Oh, sorry, I brought the wrong window. Okay, here are the other examples. So, this is the Mathematica notebook with which I computed the first computation, and here it is already shown to you. Okay? Now, let's do the same thing at t equals -1. Well, I mean, this is silly. You get the Jones polynomial. Now, let's compute the Hovanov homology of the knot 5,1 and the knot 10,132. I should have included pictures. Maybe I'll show you pictures in a moment, but let's just compute them. Okay, here's one, here's the other, they're not the same. But now if I substitute into these two polynomials t equals -1, I'll get the Jones polynomials. So the Jones polynomials of these two knots are the same. So the conclusion is that Hovanov homology is stronger than the Jones polynomial. There is no abstract reason whatsoever. It's just brute force computation. So in fact, this was, I made this computation first, and the compute, and I think until that computation, Khovanov homology might have been a curiosity, but once you do this computation, you realize it's actually stronger than Jones, and then it might be interesting. That was in 2001, about a week after September 11, in the basement of the mathematics building at in the Kyoto Math Institute. It was fun. Anyway, so the next thing I wanted to mention is, well, actually, this is a slide from well, it's from the Montreal talk, but I originally copied it from a talk I gave in 2005, I think. And the slide says, if you compute the Jovanov homology of the 7-6 torus knot, if you haven't seen a torus knot before, here is a picture. So it's basically a knot that wraps around the torus. I mean, I think you can see the torus here, right? And the knot wraps around it, and it wraps around it like 7 times in one direction and 6 times in the other direction. So, right, a torus is the product of two circles, this circle and that circle. And when you trace this knot, it goes around one of those circles 7 times and the other circle 6 times. You can check that this knot has 35 crossings, and you can estimate that a brute force computation of the Hovanov homology, like the brute force computations that I've shown you for sorry, it's on the other, for basically like the diagram that I was showing at the beginning of the picture. So it will have 2 to the 35 spaces, each of which is pretty high dimensional, and you can estimate how big they are. And then you'd have to row reduce. You have to find the kernel and the image of matrices that are, you know, roughly 2 to the 35 by 2 to the 35, or probably more. And that's going to take some time. And the estimate for how to do it, is that it should take about 1,000 years and about 1 gigabytes of RAM. So you can't do it. Okay? However, here is the answer. And furthermore, the answer at the time took 1 day on my ancient laptop, and by now with better programs it's down to seconds. Okay? So the answer is written in a different format. Instead of writing the Hovanov polynomial, I write it as a table of the dimensions. So basically the entry in row J, column R, is the dimension of the jth degree piece of the rth homology. Okay? So, as a demonstration that you...
Yeah? Do 1, 2, and 3 indicate different knots?
No, there are dimensions. What do you mean different knots?
Oh, sorry. So this is a single, just T7.
Oh, this is the Hovanov homology of T76, which is a 35 crossing knot. The overall dimension is the sum of all of these numbers. And these are the dimensions of the individual homology groups. Okay? And by the way, this is 35 crossing. By now, people have computed Hovanov homology for knots with up to 70, 80 crossings. I mean, you can do pretty far, and that would be, you know, in using standard techniques, using the technique we already know, it would be longer than the life of the universe. Something must have happened. Anyway, just as a demonstration, let's actually do the computation. So I actually tell the computer to store the current date, which actually includes in it the seconds, the time. Compute the Hovanov homology of the Taurus knot, and then compute the current date minus the stored time. So this will output the actual time that the computation took. So did I just started running it? Yes, I did. Let's wait, and let's hope nothing terrible happened. So 5 seconds. And if you look at the coefficients here, they correspond to the number here. So numbers here. So for example, like this 3 q to the 49, 2 to the t to the 13. So this 3 must be this 3. 49, and hopefully the other axis is 13. Let's check that. Yeah, it is. Okay. Okay? And, you know, as a last computation, just the number of crossings, well, I mean, you could just count, but it comes out 35. Okay. Okay. I'm done with this, and now comes the question of what happens next. So there are two possibilities, and I want your input. So one possibility is to continue with Hovanov homology, and I will tell you how this completely impossible computation is possible. And the technique is basically the same technique as for the Jones polynomial, namely divide and conquer. You cut the knot into pieces. Okay? The problem is that if you cut a knot into pieces, you end up cutting all the smoothings into pieces. So if you cut a smoothing into pieces, I don't know, let's pass a line through here. There is the upper part and the lower part, and now the cycles are no longer cycles. And furthermore, if you only look at the top part of the picture, at what's above my line, my cut line, you don't know how the cycles will close. Okay? So I mean, you have a few arcs, but you don't know how they will close. So you don't you don't yet have vector spaces, right? You have things that will become vector spaces once you know how to close them. Okay? So you end up talking about pre-vector spaces, or not pre-vector spaces, but things that have information that will later become vector spaces, along with maps between them, which are, again, pre-maps. So descriptions of things that will become maps once you figure out how to close stuff. Okay? And the words kernel and image no longer make sense. Okay? So, but still something does make sense. So the claim is that parts of homological algebra make sense even if kernel and image don't. And then we'll have to look at these parts of homological algebra and then see how it applies to Hovanov homology. So that's one choice. The other choice is, well, I'll answer, but not in a fully satisfactory way, but still the best way I have. Why is the Jones polynomial, in what sense is the Jones polynomial three-dimensional? And it turns out that the best answer I know for this is, so there is a notion of polynomials on the space of knots. So the Jones polynomial is you, for every knot, it associates a polynomial. I'm talking about something else. I'm talking about functions on the space of knots that in some sense can be regarded as polynomials. It turns out that if you study these functions sufficiently well, okay, first of all, their definition is completely three-dimensional. There is a certain classification theorem, and there is a certain construction that, given a Lie algebra and a representation, constructs such a polynomial, such an invariant. And if you take the Lie algebra SL2 and the two-dimensional representation, you get the Jones polynomial. But you could take any other Lie algebra, or not any, but I mean almost any other Lie algebra and any other representation, and you'll get a bigger and bigger family of other knot invariants that sort of look like the Jones polynomial but are different. Okay? So, A or B? And I promise that I launch a poll. It will be my first, what do you call it? Zoom poll ever, and I hereby launched it. So I want your answers.
Are we eventually getting to both topics?
Sorry?
Are we going to eventually get to both topics?
Depending on timing, I'm not promising anything because, you know, we might, but in principle we could. We have enough time to cover both topics. If we don't, it's because we'll do more interesting things. I mean, better things.
How much knowledge of Lie algebras will we need to do the second topic?
Little.
Okay.
Little knowledge, but it's much better if you're familiar with the concept, because otherwise it looks like a completely arbitrary thing. Ooh, the voting is very, it's a landslide in favor of option B. Okay, do you see the results yourself, by the way?
No.
No, we don't.
No.
Okay, it's a
I think you
landslide.
need to finish
I was
the poll and
nervous.
then share it.
It's a landslide. It's 10-0 at the moment. How many are you? 1, 2, 3, 4, you're 11. So one person didn't vote. Okay, it doesn't matter. Sorry, that person who didn't vote lost their...
The submit button for me appeared off screen and I had no way of dragging it on screen.
Okay, so you were the one who did not fulfill
Can we
his
mail in our
civic-
ballot?
Yeah, you can mail in your ballot, Jesse. Though by now it's, well, moot. Okay. So, oh my God, I'm sorry. V is a bit overused. So V is now a not invariant. It's not we're a new topic, it's a new V. Okay? So let V, and in fact V here stands for Vasiliev, the fellow who, along with Gusarov, first studied this type of invariants, but he published first. Okay? So let V be an invariant of oriented knots. So oriented just means that the knot is oriented. There is an orientation on the line. And by the way, I said knots. I didn't say knot diagrams. This is completely three-dimensional. This is not projected to the plane. It's only projected to the plane for the purpose of drawing it. Okay? Of oriented knots in oriented R3. So I want to look at a three-dimensional space with a fixed orientation on it, so that I can apply the right. So basically, I have a right hand and a left hand. Okay? And I know which one is which. Okay? And in fact, the same definition, well, okay, R3 and S3 are the same from the perspective of knot theory. Adding 1 point doesn't make a difference. But in fact, the same definition works exactly the same also in other manifolds, but we're not going to bother. Okay? I claim that V can be extended to, let me call it one singular knots via, so the definition of the extension will also serve as the formula for the extension will also serve as the definition of one singular knot. So a one singular knot is a knot that has in it one double point. So in one place, I allow the knot to self-intersect. Okay, and I mark it as a double point. And of course, since it's an oriented knot, both of these lines are oriented. And I will insist that it will be a transverse intersection, which really means that locally it looks like this. So it's not a tangency, it's an actually passing through. Okay, an actual passing through of two lines. So that's a one singular knot. Okay?
So question, so in this kind of knot, when you deform the knot, I suppose like the crossing cannot become unstuck, right? Like the crossing has to stay there.
Yeah. So, oh right, so this singular points, if you want, is put in a cast. Like you put a cast in your hand or something, or you solidify its little environment. So such one singular knots are considered up to motions, but motions that are not breaking the cast. Motions that are, or you know, this sort of is glued. You're not allowed to break the glue. Okay? Anyway, sorry, I'm running out of space. Page, append, let's append 3 more pages, came out 4, good. Okay, so now we know what's a one singular knot. Let me tell you how to define V of a one singular knot. Okay, so V of a one, you know what? Maybe even temporarily I'll call it V up 1 to indicate that it's V of a one singular knot. Okay? Now, so if you have a double point like this, there are 2 ways of resolving it. I can break it, exactly what I told you not to do. When you're deforming a one singular knot, you're not allowed to break the double point. Okay? But for this definition, you precisely do that. You break the double point, so it becomes an overcrossing. So you get a picture like this. And when I say overcrossing, I mean a right-handed, damn it, I drew a left-handed crossing. I meant you break it to be a right-handed crossing, namely a crossing such that the right-hand law holds for it. If you hold any of the strands, be it the upper or the lower, with your thumb pointing in the direction of your flow, the fingers point in the direction of the flow of the other strand. Okay, and you could also resolve this singular point into an undercrossing as something that looks like this, and in both cases you can define you can compute the original v. In both cases you get an ordinary knot, a knot with no singular points. And you can compute v and take the difference of v of the overcrossing minus v of the undercrossing. Okay? So that's the definition. Notice again, it's completely three-dimensional. This had nothing to do with the projection to the plane. The projection to the plane is because I had to draw it somehow. But you know, the two strands could be like this. Sorry, I'm using pens. Maybe I'll come closer to the camera. They could be like this, but they could be like that, or any way you want. If they, sorry, this definition makes sense completely independently of the plane. Okay, now, differences are cousins of derivatives. Okay, a derivative of a function is really the difference of the function, of the values of the function in two neighboring points, right? And in some sense, like the two knots that you get using this resolution or that resolution are two neighboring knots. I mean, they could be huge, but they differ in only one place. So this is like a derivative of the original invariant. So v up 1 is the first derivative of v. The moment you have first derivatives, it's tempting to think about higher derivatives. So I could define v up m of a knot that has m double points. So suppose it has m double points. So this is m. And such knots will be called, you know, something, I don't think I left enough space. Here is something you cannot do with an ordinary blackboard. So such knots are called M singular knots. And I don't think I really need to define. It's like a one singular knot, except it has M of those singularities. Anyway, you will define v up m of an m singular knot to be v up m minus 1 of the knot that you get by picking one of these singularities and resolving it. So basically, you'll take the first double point and replace it by an overcrossing, keeping all the rest, and then subtract v up m minus 1 of the knot that you get by replacing the first double point by an undercrossing and keeping all the rest. Okay? Now, you can complain that the definition appears to depend on which double point I chose to resolve. Okay? But actually it doesn't. And for two reasons. One reason is that, well, we've actually switched to multivariable calculus now, and this is like the mth derivative refers in different places. And in calculus, you know that partial derivatives commute, partials commute, so it doesn't matter. So if you resolve this one and then that one, or resolve this one and then that one, you get the same answer. That's partial derivatives commute. That's of course not a proof because these aren't derivatives, but if you look at the proof why partial derivatives commute, the reason why partial derivatives commute is because basically if you take the difference between this and that, and then take a difference of such differences, so you end up looking at like 4 points, and they all come with different signs. It doesn't matter if you first regard it as a difference, well, as in each row a difference and then the difference of the rows, or in each column a difference and then the difference of the columns. This is what the partial derivatives commutes boils down to. In the case of knot theory, it's even simpler, because here you need to add some analysis, like limits, etc. We don't even have to do that. So if you have a knot with 2 double points, and you resolve the first one first and the second one second, or the other way around, in both cases you'll get 4 answers. So you'll get V of both are replaced by a positive crossing minus V of one is replaced by a positive crossing and the other by a negative crossing minus V of, let me be a bit more schematic now, so that was plus plus, that was plus minus, minus V of minus plus, and plus V of minus minus, and you'll get the same combination no matter which one you resolve first. Okay? Alternatively, I could simply resolve all the way. I could simply say that V up M of a knot with M double points is the sum of, so let's give this knot a name, K, okay? It's the sum over all choices of signs, S, which lives in the n-dimensional cube, sorry, M, not N. Okay, so basically a sign for each crossing of basically the product of these signs multiplying V of the knot that you get by resolving each crossing according to the sign specified here, so I'll call it K sub S. Okay? So basically we saw here an example with 2 crossings, but I could have done it with M, and there is just one single answer. If you have M crossings, V up M of, sorry, M double points, V up M of such is given, well, each one can be resolved in 2 ways. You have 2 to the M resolutions. The sign, well, I have nothing to add about the formula. I also only have 1 minute to continue, to complete the story, well, not to complete, for today. So I'll just make a definition. So just like polynomial, what's a polynomial on Rn? It's a function all of whose m plus, sorry, it's a polynomial of degree m is a function whose derivatives of degree higher than m are all 0. Okay? So definition, V is poly of degree m, but now this is polynomial on the space of naught. It's a polynomial as a function of the naught. Okay? If the m plus first derivative of v is identically equal to 0, meaning no matter which naught with m plus first double points you feed into it, you get 0. That's the end of today, but the point will be to study these. And it turns out that there's a lot to say.
Sorry, what is B?
B? Oh, this? No,
Yeah.
this is the English word is. Sorry, I was writing so quickly that it came out funny. Other questions, comments?
Yeah, could you move up a bit?
Me?
Oh no, that's the word.
Sorry, I'm just being silly. Yes.
Yeah,
You know,
so
I actually have a stool here. Yes.
the V double points, two double points equal to this, the summands you have there.
Yeah.
Are they equal? No, the minus plus minus, are they, can we regard them as the same or not?
No. I mean, these represent two different crossings or two different double points. They lie in different places. So, right, if this was, you know, here is an example of a knot. Oops, sorry. Here's an example of a knot with two double points. God, what did I want to do? I don't know. Here is an example of a knot with two double points. Okay? I mean, resolving this one and resolving that one is not the same. Replacing this one with a plus and this one with a minus, or this one with a minus and this one with a plus, is not the same. You get different things.
Okay.
So these four knots are potentially all different. Of course, by coincidence, they could be all the same. Or some of them could be different and some could be the same. But generally speaking, these are four different knots. And here, generally speaking, these are 2 to the m different knots. Other
This
questions?
Jones polynomial will also have some degree, right? If it is a poly Vassiliev invariant, is that,
So,
considering you said that's an example of things we can construct out of?
so the Jones
Yeah,
the Jones polynomial in itself is not a finite type, a polynomial, a Vassiliev invariant, but sort
I
of
see.
like, you know, like in the case of Khovanov homology, each coefficient considered separately, once you make the appropriate change of variables, will be. So the Jones polynomial is not of that type, but it's equivalent to something else which is of that type.
Oh, okay, because the number of moves you need to go down is the degree of that coefficient, because then the Jones-kind relation allows you to break it into.
Roughly, you're roughly correct, but I'll have to say a bit more.
Okay.
Okay? By the way, at this point I don't particularly care about the Jones polynomial, right? I have a completely general theory. Well, it's not yet a theory, it's a definition. I mean, it could end up being the empty definition, but it's clearly worth studying. And in fact,
I
it's
just want
much...
to sort of picture it in context, picture the Jones polynomial in context of this.
Yeah,
And now
but we will connect it with the Jones polynomial in time. And by the way, this is much more general. This really doesn't have much to do with knot theory. I mean, the same thing can be done in many other places, and is done in many other places, where you look at neighboring objects and look at differences and then iterate the differences. I mean, it doesn't have to be knots. It could be manifolds. It could be two-dimensional knots in R4. It could be...
Right.
In fact, I'll give other examples later it could be completely unrelated to topology. It's a general sort of phenomena that you can talk about polynomials, not necessarily on Rn, but in fact on various combinatorial spaces.
It feels almost like if you have any topological space and any open and dense subset, then you can define this polynomial as like when you pass through the when you pass through the boundary of this set, you have to take the derivative or something.
There is some, yes, I suppose, there is something along these lines too. But anyway, of the many such polynomial theories, knot theory turns out to be one of the most successful. But at the moment you don't see it yet, we still have to demonstrate it. Okay, people are already leaving, they must be going elsewhere, so let's officially turn off the video, and that's the end of the class.